Let's study about electric field due to continuous charge distributions. Charge distributions. There are two kinds of charge distributions. We can say discrete, other one is continuous. Discrete charge distributions, that means we can take single, okay, because this electric charge is quantized in nature. That means there are only, suppose you take one electron, okay, the charge of that will be q is n times e. Here n means number of electrons, you can write 1 here. Suppose the two electrons, you write 2, we can't write 1.5 and all, so n is just a numbers like this way, 1 2 3 4. Then next one, let's take 3 or 4 charges. Let's take 3 charges here, and there's a point here p. Let's name this charges q1, q2, q3. It's q1, q2 and q3. At this point q1 will give an electric field, that is E1, okay. So q2 will give an electric field, that is E2 vector. Then q3 will give an electric field, that is E3 vector. So total electric field we found that is electric field is equal to E1 plus E2 plus E3, okay. And we found that is 1 by 4 pi epsilon naught q1 by r1 square r cap and all we learned in electric field due to point charge distributions. Let's come to continuous charge distribution. There are three kinds of continuous charge distributions. One we can say linear charge distribution, other one is surface charge distributions, third one is volume charge distributions, okay. So what's meant by the continuous charge distribution? That means if we take a, say, an aluminum foil like this way, okay, if I give a charge to it, that means we can't say only 1 or 2 electrons, there will be many millions of electrons in this, okay. So it will have a lot of electrons, and these electrons are continuous in nature, okay. You can't say this electron is here, that electron is here. So that's meant by continuous charge distributions. Let's study this continuous charge distribution more in detail now. Now let's study electric field due to continuous charge distribution, okay. Now let me take an irregular object, okay, and let this point be P here. So let's see what are the electric fields due to this object here. So this object we given many electrons, many charges. So let me take a small charge here, okay. The textbook is drawn as a box, we take a small charge. Let this charge be delta q1, okay, small charge here, delta q1. Now next one, so you can see at this point another charge we can take, that is delta q2, and at this point we take this as delta q3, okay. So electric field due to delta q1 will be coming downwards like this way, and this electric field we mark it as E1 vector. The distance between this delta q1 and p will be r1p vector. Then the electric field due to q2 will be coming this way, and this electric field we can mark it as E2 vector. The distance will be r1 r2 p vector. Then the electric field due to q3 will be coming downwards like this way, and in this direction this will be E3 vector. The distance will be r3 p vector, okay. Now let us see what will be the total electric field. We learned that from the last one, that is electric field due to discrete charge distributions, the electric field will be equal to E1 plus E2 plus E3, and we got that for that one we got 1 by 4 pi epsilon naught into q1 by r1 p the whole square into r cap 1 and p. But now here we see we have small charge here, so we write as delta q1, that's the only difference here. The next one, write as delta q2 divided by r2p square into r cap 2 and p. Then plus it goes up to plus delta qn by r n and p the whole square into r cap n and p, okay. Now what we do is we can take summation, okay. So write it this way, 1 by 4 pi epsilon naught into summation of delta qi by ri p the whole square into r cap I n p. Now what is I mean? I will start from I is equal to 1 to n. This is I. So this is electric field to continuous charge distribution. Now, but what happens is, this is only, they say approximate, it's not exactly equal, they say approximate. This is approximation symbol. But now you see, when we take many millions of charges, we can write as an integration form. Let me write this here. So we can say electric field E is equal to 1 by 4 pi epsilon naught into integration of, instead of writing delta Q, I write as dq by, this will be r square into r cap vector. Okay, so this will be the electric field due to continuous charge distributions. Okay, and this one we are going to use it in our next formulas. That's for surface charge distribution, linear charge distribution, and volume charge distribution. Let's now study about linear charge distribution. Let me take a wire here. Okay, now in this wire, if I give a charge to it, okay, there will be many charges, many electrons or positive charges, they will be in a single line only. Okay, so this we can say as a linear charge distribution. Let me draw it for you. So we have a wire here. Now let us give positive charges to this. Okay, so I give many charges here. The charge, let the charge be Q and the length be L. Now we can define linear charge density. Let me write for you. Linear charge density. Okay, that is lambda is equal to Q by L. Okay, you can see charge by length. So let's see what will be the SI unit for this. That is, charge is given as coulomb, length is given by meter. So SI unit is coulomb per meter. That is the SI unit for this. Okay, now let me take a small region here. Okay, so in this small region, I will mark it as, this small region as dq. The charge on this region will be dq. The length, corresponding length will be dl. So we can write linear charge density in this case as lambda is equal to dq by dl. Okay, now cross multiply here. So we get here lambda dl is equal to dq. Okay, rearrange, we get dq is equal to lambda into dl. Okay, now what I'm going to do is, let me substitute in the formula. Okay, so we know the formula for electric field. So I'll write here, that is electric field formula we got, that is 1 by 4 pi epsilon naught into integration of dq by r square into r cap. Let me write this, substitute this formula here. Now let me take this formula and write down here. So that will be E is equal to 1 by 4 pi epsilon naught into integration of dq. Instead of dq we have this lambda dl by r square into r cap. Okay, this gives a electric field for linear charge. This gives electric field for linear charge distribution. Now let's see surface charge distribution. So for surface charge, I'll take a, say, an aluminum foil this way. This is the shape of a square. We give charges to this, okay, and it has an area also. Okay, let the charge be Q and the area be capital A. Okay, let me draw it for you. So we take a aluminum foil. The charge given to this is Q. The area of this will be A. So in this case, we can say surface charge density. Surface charge density. Okay. So that will be equal to sigma. Sigma is equal to Q by A. Let's see what will be the SI unit. SI unit of charge is coulomb. SI unit of area will be meter square. So its SI unit will be coulomb per meter square. Okay. Now let's see, we take a small area here. Okay, very small area. The small area we write as dA, and the charge on this will be dq. So in this case, the surface charge density will be dq by dA. Now cross multiply here and rearrange, we get dq is equal to sigma times dA. Okay. Let me write this in the formula here for electric field. So electric field will be equal to 1 by 4 pi epsilon naught integration of sigma dA by, sorry, this will be by r square into r cap. Okay, now let's go to volume charge distribution. Now let me take a sphere. Okay, this is a metal sphere, and on this metal sphere I'm going to place a charge. Okay, so when you give a charge, the charge will be on fully on the metal sphere. Okay, its volume will be V and the charge is Q. Let me draw it for you. So we take a metal sphere, the charge that we given is Q and the volume is V. Now we have something called as volume charge density. Volume charge density. So volume charge density is given by rho. This is a Greek symbol for rho. So rho is equal to here charge by volume. Let's see what's the SI unit for this. That will charge, SI unit of charge is coulomb. SI unit of volume is meter cube. So coulomb per meter cube. This is the SI unit here. Now let's take a small region here. Okay, you can take anywhere. So let me take a small region. So in this thing, so this will have a charge here, that is dq. So dq is the charge and the volume will be dv. Okay, now so charge volume charge density we can write as rho is equal to dq by dv. Cross multiply and interchange, so we get here dq is equal to rho times dv. Okay, so let me write in the formula for electric field. So electric field E will be equal to 1 by 4 pi epsilon naught into integration of rho dv by r square into r cap. Okay, but if you notice that what's the most important thing is the three things: linear charge density, surface charge density, and the volume charge density. Let's compare them. So lambda is equal to q by L, that's linear charge density. Surface charge density is sigma is equal to q by A, and then the volume charge density is rho is equal to q by V, charge by volume. These three things are the very important things that we're going to use in our coming classes.